The next big topic in this chapter is energy. Energy is a little hard to define. It's easier to talk about examples than it is to come up with a general description. However, you can start by thinking of energy as that which makes matter move. As we look at it more closely, it will be easier to see what this means. We usually divide energy into three broad types: kinetic, potential, and radiative. Radiative energy is just another name for light, so we'll look at that when we talk about light later in the course. Just remember for now that light carries energy.
We experience a lot of different units of energy in our lives. We buy electrical energy in units of kilowatt hours. We also get heat energy from natural gas in units of British thermal units, or BTUs. And of course, when we look at the energy content of food, we usually measure it in calories. So yes, the calories in lunch are really a way of telling you how much energy is stored in it.
We can use any of these units to measure any kind of energy. However, the unit for energy that we'll use in this course is the joule. A joule is really a kilogram meter squared per second squared. So it fits well with the sort of units we've already been using. In fact, it looks almost the same as the force unit, the Newton. The only difference is that the meters are squared in joules. Notice that if we want to use joules as our unit of energy, it means we'll have to always make sure we've got masses in kilograms, distances in meters, and times in seconds. If we have any other set of units, we'll have to convert them, or the answer will come out wrong.
Since we're using joules, here are some values to give you a sense of how much you can do with a joule of energy. On a sunny day, there are roughly 1,000 joules of energy hitting every square meter facing the sun every second. On the other hand, a typical candy bar has about 1,000,000 joules of energy. As it happens, that's roughly the amount of energy the average person uses if they walk for an hour. It's also how much energy of motion a car has if it's going at 60 miles per hour.
As you look down the list, you'll see the numbers getting bigger and bigger. Remember that with numbers written this way, it's the exponent that's the most important part of the number. That total daily energy used by an adult, 10 to the 7th joules, is 10 times as big as the energy from one candy bar. Always watch those exponents. Our first type of energy is kinetic energy. This is really just the energy contained in a moving body. If something crashes into you, then the amount of energy it gives you is equal to its kinetic energy.
The amount of kinetic energy is given by 1/2 times the mass times the velocity squared. That's all. The amount of kinetic energy does not depend at all on how the object got moving that fast, or how much gasoline is in its gas tank, or on anything else. All that matters is how big it is and how fast it's going. Also, kinetic energy is not used up by motion. In other words, you don't run out of kinetic energy just because you've been traveling for a long time. If you are slowing down, it does mean that your kinetic energy is changing to another form of energy or being transferred to another body, but it doesn't just disappear.
Of course, this ties in with what we saw with Newton's laws. Remember that first law of motion? Go back and check it if you don't remember it. Got it? It's the one that says a body in motion stays in motion unless acted on by an outside force. We saw that the reason things slow down on Earth is because they're experiencing the force of friction. From an energy standpoint, we say that things slow down because friction converts kinetic energy into heat, which we'll look at more on the next slide. This idea takes some getting used to, which is why Bruce is dropping in to remind you to be careful about this. One special case of kinetic energy is heat. If you could see the individual atoms in the matter around you, you'd find that they're all moving very rapidly. Whether you're looking at a solid, liquid, or gas, the atoms all have some motion, though in some cases all they can do is vibrate in place. The sensation we know as heat is really just the average kinetic energy of those atoms. So if something feels hot, it means that the atoms it's made of are moving very fast, while if it cools down, that means its atoms are slowing down.
If temperature depends on how fast the atoms are moving, then there must be a minimum temperature, a point at which the atoms essentially stop moving. Nothing can get colder than this, since you can't go slower than stop. The Kelvin temperature scale is based on this idea. The 0 point of the scale, 0 kelvins, is absolute zero, the temperature at which atoms stop moving. This is equivalent to minus 273 degrees Celsius or minus 460 degrees Fahrenheit.
We won't ask you to calculate conversions between these three temperature scales. That's just not worth the effort for what we have to learn here. But you should get familiar with a few numbers just so that you have a sense of what Kelvin temperatures mean. So water freezes at 273 Kelvin. If you know the Celsius scale, then you'll know that this is the same as 0 Celsius. Water boils at 373 Kelvin. But perhaps the most important number to remember is that room temperature is around 300 Kelvin. If you keep that number in your head, you'll have a good idea of what it means when we start using Kelvin temperatures. So if we say that the surface of Titan is 93 Kelvin, you should be thinking to yourself, room temperature is 300 Kelvin, so 93 Kelvin is damn cold. If you can do that, you've got a reasonable sense of what temperatures in Kelvin mean.
There is one more idea related to heat that we should look at, and that is thermal energy. Thermal energy is the total amount of heat an object has. This certainly depends on the temperature, but not just the temperature. It also depends on how many atoms the object has. As a result, something can be very hot, meaning that its atoms are moving very fast, but still not have much thermal energy because it doesn't have many of those atoms.
An example of this happens in the Earth's upper atmosphere. 200 kilometers up, the air temperature is quite warm. But if you were to stick your hand out there, it would probably freeze. This is because the air is incredibly thin, so very few molecules hit your hand to transfer heat to it.
The next type of energy we should look at is potential energy. To understand potential energy, we have to start with something called the law of conservation of energy. This law says that energy cannot be created or destroyed. In other words, you can change the form of the energy, but you can't get it from nothing, and it doesn't disappear into nothing. In the early 20th century, physicists found that you have to have a very broad sense of what you mean by energy in order for this to be true, but we'll get to that a little later.
While energy can't be destroyed, it can be stored, and that's what we mean when we talk about potential energy. Potential energy is another way of saying stored energy. So how do you store energy? Anytime you move something against a force, you store energy. For example, when you lift up a ball, you're storing energy in that ball because you have to push upward against the force of gravity to get it above the ground. There is one exception to this: friction. When you push against friction or other forces like it, such as air resistance, you don't store the energy. Instead, as we mentioned earlier, that energy is converted into heat. Try rubbing your hands together very quickly for a minute. You'll find that they get quite warm. This is an example of friction turning kinetic energy into heat.
There's Bruce stopping in again. Whenever you're thinking about energy in a system, don't forget the friction. That's usually one of the most important reasons that things lose kinetic energy.
There are many different forms of potential energy. So when you describe how energy is being stored, it's important to say what form of potential energy is involved. We've already seen one type of potential energy, gravitational potential energy. This is the energy stored in a body as it goes uphill. Anything that has the potential to fall has gravitational potential energy. This is an important one in astronomy. A lot of astronomical processes depend on gravitational potential energy, so we'll be seeing this one a lot.
Elastic potential energy is energy that is stored in materials that have been bent or squeezed or twisted or so forth. When you stretch a spring or squeeze a ball, it stores elastic potential energy.
Chemical potential energy is the energy stored in chemical bonds. If a chemical reaction releases energy, then there was stored chemical energy in the system. For example, anything you can burn has stored chemical energy. Also, the calorie count in foods is a measure of their chemical potential energy. In fact, the traditional way of measuring the calories in food was to burn it and measure the heat produced.
Finally, electromagnetic energy is the energy stored in electric or magnetic fields. The most common way to experience this is with anything powered by electricity. There is electric potential energy in a wall socket, so when you plug an appliance in it, it converts that electric potential energy into another form of energy.
Now that you've done that problem, here's a more challenging one. Once again, we're applying the ideas we've just looked at, this time to a car driving down the road. There is a little calculating here, but only in Part A, where you're looking at the rate of energy use. In Part B, you don't have to do the kinetic energy calculation, but you do have to remember that kinetic energy depends only on mass and speed. Finally, Part C is the one where you should explain what's really going on here. There is one more form of potential energy we need to look at, and that's mass energy. Mass energy is crucial in astronomy. It's the power source for stars, and it's also important for providing heat to the interiors of some planets. Mass energy is a direct result of the special theory of relativity. One of the key discoveries of the special theory was the idea that mass and energy could be converted into each other. The equation that relates mass and energy is probably the most famous equation in physics, E equals mc squared. What this formula says is that you can turn a certain amount of mass, m, into energy. The amount of energy you get is given by the mass multiplied by the speed of light squared. The speed of light is a big number, so the speed of light squared is a huge number. As a result, even if you're using very little mass, it still produces a tremendous amount of energy. Let's take a look at how we calculate mass energy. Imagine you could turn 1 kilogram of matter into energy. It turns out this isn't very easy to do, but if you could, then the amount of energy produced would be given by putting this mass into the mass energy formula. So we write down the equation, and then we substitute in 1 kilogram for the mass. When we multiply it by the speed of light squared, we get 9 times 10 to the 16th joules. Notice that I haven't said what that 1 kilogram is made of. It could be hydrogen, or helium, or carbon, or peanut butter. It doesn't matter. If you can convert it all to energy, that's what you get. So how much energy is 9 times 10 to the 16th joules? Well, it's about the same amount of energy as exploding 20 million tons of trinitrotoluene, or TNT. This is about the energy of the largest hydrogen bombs tested during the height of the Cold War. In fact, hydrogen fusion is an example of releasing mass energy. Alternatively, you could say that this is the same amount of energy as you would get from burning 3 million tons of coal. To get a picture of how much coal that is, have a look at this train. A typical coal carrier on a train holds 100 tons of coal. So if a typical train like this is 100 cars long, that would be 300 train loads of coal. In fact, we can only extract mass energy from nuclear reactions. So getting at all that energy is not easy. Later in the term, we'll look at some more specific examples of mass energy in astronomy. Now it's your turn. Go ahead and try calculating the mass energy that the Sun will produce over its 10 billion year lifespan. Notice that I haven't given you all of the information you need. You'll have to look up a couple of things before you can do this calculation.
Remember this table? You should be using it to help you keep track of the equations we use in this course. Fill in the E equals mc squared section of this table now. Keep it and update every time we use a new equation. You'll find this page useful doing homework and reviewing for exams. Depending on your section, you may be required to submit a copy of the completed version for credit. Now you should fill in this table about energy. Simply define each of these major types of energy. If you've learned an equation to go with it, add that in here too. We've mentioned some astronomical examples of some of these, and you may be able to think of others. Leave some space in that last column to add more as you come across them later in the course.
You may have noticed by now that most of the interesting things that happen with energy are a result of objects converting energy from one form to another. See if you can describe objects that are converting energy between these different forms.